It's really great to be here in Hamburg. And so I think the talk, for many of you, I'm sure, watching, will be obvious in parts and not so much in others. And actually, I actually made it fairly informal. So there may be opportunities to ask questions throughout, maybe for ease. Guys, maybe you might do all at the end.
It's on you.
Yeah, so actually, it's whatever you guys want. So if there's sections in between, generally 4 sections here that I'm going to be talking about in spatially embedded recurrent neural networks, which is some of the work that I did toward the end of my PhD. And I think it spurred on a few new ideas that I think intersect with lots of what you guys might be interested in working on. So I'm first going to start a little bit about thinking about structure and function in neural networks before going into what the spatially embedded recurrent neural network is and what we found in our kind of work. But I kind of see it as fairly early investigations that has now spurred on quite a lot of new ideas, particularly around communication models, optimization in neural networks.
Okay, is that better? Hello, hello, hello. Yeah, no problem.
Yeah.
Okay, is that good? Yeah, great. And then I'll kind of talk about this kind of some speculative ideas as well. So I'll just throw out some things and we can discuss it. So investigating structure and function in artificial neural networks. So I think when a lot of us think about this distinction between structure and function, at least for me, when I think of structure, I think of what is it that's clearly observable through our experimental protocols, perhaps through our neuroimaging devices, things that are very clear structural or microstructural properties. In the network neuroscience world, we might think of actually from the macroscopic level, at least, a kind of 3D geometry, but actually, of course, that holds directly down to the microscale structure. We might think of something like connectivity length dependencies. You may have heard of this idea of like a wiring economy, the idea that, we have non-random connectivity lengths within the brain, and there's various hypotheses that this is put down towards, and wiring motifs. So this is actually a lot of what I started focusing on in my early PhD. But then, of course, we don't just have structure, we have this idea of function, that we make this dichotomy. And so generally, when I think of function, I think of this idea of general problem or task-solving systems. We've evolved and developed numerous functions to be able to solve problems in the real world. It's ultimately why we evolved, to be able to solve problems. And that we can make decisions and actions within an environment. And whilst we make this clear distinction between the two, it's not obvious how to kind of tackle the questions that interact between the two ideas of structure and function. And some of the questions that I was quite interested in was to ask things like, how do structure and function interact directly? Do they shape each other? And if so, how? And what features arise from their interaction that can't be explained solely within one framework? So what have people done? So I kind of break them down in my mind within 3 ways, but actually there's actually quite a few more when I was writing this talk. So you might ask a question like, what are the associations between structure and function, right? You might say, if I take the structural connectome and the functional connectome, how are they correlated, right? Or you take some observable associations between 2 features that you can observe experimentally, for example, and that would be some sort of associative approach. Another might go a little bit further and might say something like individual differences. You might say, how their individual differences in some neural feature vary with some individual differences in behavior. And here, by the way, I'm kind of conflating behavior and function. But we can come back to that later. But here you can actually have maybe some causal evidence. You might be able to say, how does a stroke change behavior, for example, which might be some neural change and some change in behavior. And of course, which will be the topic of this kind of talk, will be on computational models. And I was quite interested in thinking about how, if we embed structure and function directly within a model, and you mathematically formalize this in some way, is there anything interesting that just kind of appears? Or is there something interesting that becomes obvious to you after the fact? And obviously, I'm going to talk a little bit about this. Models that can kind of deal with structure and function together. And then this actually, hopefully, will spur on a few more questions. So on computational models of structure and function, I'm kind of in the right place. Because obviously, in your lab, you've kind of been working a bit on this. So on the one hand, what typically you kind of see is that you would specify one structure or function and see what emerges within the other. So you might say, for example, if I were to embed within a reservoir computer some structural prior, such as obviously the work within your lab that I kind of placed out here with bio to art, for example, so biological data to artificial data. What is the functional sequelae? the consequences of this. In contrast, and of course, this is great work that you can look at different topologies, you can look at weight relationships, and Fatima was talking about this earlier, and lots of different great work on thinking about what structural priors leads to some functional consequence. An alternative approach might be not to say what the structural prior is, but what a functional prior might be. So some of you might actually be interested in thinking, well, actually, a lot of these structural outputs like modularity or clustering or some sort of organization comes not from the structural priors themselves, but they actually come from the evolved functions that we have to do. And so in this paper by Robert Yang, there's now the canonical paper on multitask recurrent neural networks in Zhejiang Wang's group. They just tested, basically made a way such that RNNs wouldn't exhibit catastrophic forgetting by adding a cool regularizing in there. But basically, sorry, that. Oh, sorry, I'm skipping ahead a little bit here. And what they did was effectively train their RNN on a gambit of tasks. So now you actually have to have a neural network that is learning a curriculum of tasks. And then what you see here, hopefully you can see my pointer, is this is a t-SNE of the neural activity patterns. And so effectively what they're saying is that you get clustering of neural activity patterns as a result of training on lots of different tasks. So they're kind of doing the opposite. If you train the network to do something, what are the structural outcomes that you get as a result? Although this is not structure exactly in the same way. This is what you'd say structure of the functional activity patterns, as opposed to the topology that you might think of. But the same essence holds. It's what prior do you put in and what do you read out? And so one of the kind of things that I was thinking about was we kind of have this idea here that we have a framework to test, but in the real world, it's not a clear distinction between structure and function. These are actually operating on subtly different timescales. They're different observable entities of this computational system, at least, that we're modeling. Is there a way that we can combine these two concepts together? And while I'm going to kind of talk about the spatially embedded RNN, I think the idea here is a little bit deeper than just what I'm going to present. It's actually this idea that maybe we have competing trade-offs, ultimately, which is the idea that I'm going to come back to towards the end. And how we can model that within a more realistic biological framework. Okay, so this is what motivated this idea of a spatially embedded RNN. Okay, so the goal that we kind of set out was to try and build a model that trades off what we kind of call here three-dimensional structural costs with some functional requirements. It's not that you kind of take the structural prior and add it in per se alone. You actually have a conception of this kind of trade-off. And the way that we did this was through a recurrent neural network. So many of you will know, of course, so I won't bore you, but the basic essence is that in the models I'm going to show you, we have some inputs that relate to some task variables, and we have one single hidden layer is all that we do for this, and where ultimately now we have recurrence within the connectivity, so you can have a hidden layer, which can have some connectivity between them that we investigate, and that operates over time. In our RNNs here, it's a discrete time, vanilla RNN formulation, and here's some output, and I'll tell you about the task and so on in a moment. The basic idea between the RNN is that you can do sequences, and it's a very basic model for doing so. So what did we want to add in? How did we kind of think about this? Well, we kind of took a very simple approach, and of course, as I said, it'll lead to lots of other questions that we can discuss. But we wanted to kind of put in some minimal assumptions into our model as some kind of prior. And one was in 3D space. And so a little bit about my work before had been thinking of networks not as topological networks, but as this quote-unquote topophysical networks. The idea that they have a structural, spatial location, that's actually relevant, right, at some level. And we know that generally networks favor shorter connections if you do these kind of correlations. But of course, this is nuanced with long distance connections and so on. But generally speaking, you have those kind of trends that said that we kind of sit between this kind of regular to random topology, which I'll bring up a little bit later. But that's the first very basic statement. The second is this idea of local communication. So in some of the models that I'd been working on previously, it seemed to be that the models that looked really quite elegant were ones related to something called communicability, which we've already talked about here for those of you who are not with us in person, who are listening at home. But we'll kind of probably talk about this a little bit later. But the idea ultimately being that in a normal recurrent neural network, weights just change so that you can optimize for your task. So you effectively have your loss landscape, and you descend down that loss landscape according to an algorithm such as backpropagation through time. the notion of where those weights, the reason why those weights are being driven down is due to a loss signal from the task. It's got nothing to do at all with the actual where those weights sit on a network. There's no properties of neurons communicating within these. It's just that weights are being moved in a direction so that when you do your forward pass on your RNN, that you actually can solve it well. So we wanted to capture this idea that in biology, neurons do communicate, and the extent to which weights are changing is some function of those two neurons interacting. It's as simple as effectively that there is some sort of local communication going on, generally speaking. We're not necessarily concerned with the particulars per se yet. It's just that the fact that that's the point. And the last is that ultimately we're under task control. So one of the criticisms, obviously, of network neuroscience is that you can look to network properties of the brain, or you can look at some aspect of some observable feature, and you just assume, therefore, that it's important. But that's not true necessarily. Ultimately, we are a task-solving system that has to do stuff, and actually there might be something to learn. So we wanted to basically build in a task into our models. So that's the three basic ingredients here. And we did it in these fairly simple ways. So the first was simply to take the RNN and to give each neuron arbitrary coordinates in space, where now you can have a Euclidean distance between. Now you could imagine different topologies. When we first started, different geometric arrangements of these neurons. That'll become relevant later on in my speculative idea, perhaps. At the moment, we thought because this is ultimately a Euclidean distance matrix that is symmetrical, it won't really matter the particulars of the shape. It's just the fact that it's a shape. It's the fact that it is a distance. But we'll come back to that perhaps later. The second that we did was to incorporate this weighted communicability term, which effectively is telling you a broadcasting model across that network. And so for those of you who kind of, new to this kind of phenomenon, the idea effectively is that suppose that you have a random walker that kind of operates on your network graph. And the idea is that it somehow captures the idea that information at some level has to be transmitted across the connections across that graph, right? Particularly not with, and because a broadcasting model, it's the idea that you don't necessarily need to quote unquote know where you're going. You're just kind of going out there through the network. And there's many different forms of this, and I'll talk about in a moment. But in our model, we used a weighted communicability measure, which was normalized, because in the literature, the idea is that the classic model is susceptible to a single weight can actually generate kind of artifacts. A single large weight can actually bias the whole measure. So in this example, we use a weighted and a normalized version, but we'll probably come back to that later. The last one is task control. So this is kind of relevant for some of my results later. So hopefully you can see some colors in the corners. Can you see these little colors? Hopefully. When we started this project, it was just before COVID, actually. It was actually just around the time, and we were going to inherit some really nice electrophysiological data from macaques doing a saccade task, and it was a step inference. And our plan was that we were going to actually use that data. COVID hit and never materialized, unfortunately, but we did use the task that the monkeys were doing. And so this task is effectively a one-step inference. It's very simple. So the idea is that you have to observe a goal location early on in the task. So in this case, it's in the top right location of the maze. And then that goes, so it goes away. And then you have a period of delay. So you have to memorize that the goal was in that particular location. And then you have to later then decide left or right and to go towards the goal. And so effectively, it's not a pure association. You're not just recapitulating what you saw. You have to make some very basic inference. The idea is that you're ultimately kind of subgrouping your goals into two paths, and you're knowing that you have to go right. So hopefully you can see that you would go right in this example. Okay, you can make this task harder by, for example, making the delay period longer. And you can hopefully see that that's why you require recurrence, because you now need to memorize something. And that's the basic essence of what an RNN would do. Okay, so how would we incorporate these? Effectively, all we did was state that the communicability and the distance models, those matrices, also have to be learnt in the task. So what do I mean by that? You would have a typical L1, and the inputs are just relating to the goal locations and the choice decisions. And effectively, the loss function is telling you what the network learns. And so now what we would say is that their loss has a task component. You have to solve the task. But what I kind of conceptualize this as you also have this kind of structural cost this other element that's not a task in the world that you have to solve, it's an internal problem. And that's how I kind of think about these things in terms of the trade-off analogy. And within that, we want to minimize distance. And what I would say here is to minimize communicability. And maybe we can discuss exactly why this formulation and not others in this element. But to start it off, it's the idea that you ultimately are solving other problems that aren't just the task.
Why do you want to minimize communicability and not maximize?
I have a plot that I put in exactly for this. But it's a core, a really important question, obviously. So the original way that I thought about this and why I put it in the first place was using my gradient descent analogy earlier. That you have your weights you can imagine that you have your graph of your neural network, and the weights are going up or down in whatever way is to minimize the task. I wanted the weights to change not only as a function of the task, but also as a function of to what extent these two nodes actually influence each other. And so the original formulation, actually, I wanted just to have W multiplied by the influence, which was C, basically. So that was the kind of thing. But then when you kind of speak to more machine learning people, they're like, well, why are you minimizing this term? And I didn't think of it as minimizing, but then it has interesting effects. So, and we show the inverse later, and it came to realize about these ideas of normalization, which I'll bring up. Okay, so what we can do then, hopefully you can appreciate, is that you have a lambda here, which is typical in regularization. And that lambda is just a scalar which will tell you the strength to which you will impose that constraint or not. So if lambda is 0, you are not doing any, you're just minimizing the task. And if you have a large lambda, you are doing lots of the constraints. Okay, and what we wanted to do was just see what comes out of these networks, right? So we wanted to say, okay, is there anything interesting structurally? Is there anything between the structure and how it functions that could be interesting? Is there anything functionally alone? And do you find that they converge together? And we found some quite interesting findings that then spurred on lots of new questions for future work. So first on the structure. So the classic two things that we wanted to see first was, okay, we're minimizing the distance. So we should find that there should be this negative correlation between weights and distances. That's like a validation because we've trained it to do that. But what other structural elements should appear? And it's going to start off becoming obvious, and hopefully it becomes a little bit less obvious as the talk goes on. So the first two things that we wanted to look at were just the basic elements. Do you find modularity and small worldness in these networks? They weren't directly trained to generate these, but you could assume maybe they would, maybe, because we've added in some optimization of the communication somehow, and we've done some optimization of space. So what we wanted to do is to look at that. So what you can see here is a validation ultimately. This is the hidden layer of the RNN in the three-dimensional space that we trained it, and we use ReLUs. And you can see here as an exemplar network that it has a negative correlation between its weights and the Euclidean distance, just to say that shorter connections generally are stronger. So that's nothing too surprising. So the first thing to say is that these networks you prune. So you can initialize them in different ways. In our case, the general normal way is that you prune these networks. You start them as large random ones, and then you prune them as it's minimizing some task signal. So in pink is these spatially embedded RNNs, and in L1 is like our control one. And later on we include some more controls, which I'll show you. So this is all normal. And so what you find here is that you generally will get more modular networks in the spatially embedded RNNs and slightly more small world networks in the SERNNs. Now, there's 1,000 networks have been trained here for the pink ones and 1,000 for the green. So it looks like there's not much distance on the error bars, but there is actually quite a fair amount, which I'm going to show you later. This isn't too surprising, after the fact. We've imposed a spatial structure, and we know that spatial structure is going to generate modular networks at some level. You're going to prefer things that are close, and you're going to form somewhat some clusters. And as a result, you may expect that you're going to get this kind of small world outcome. So effectively, we've done this kind of spatial and communicability optimization. Maybe not too surprising that we've got this, but maybe it is, right? It's obvious. It's obvious after you've done it. And the next thing I wanted to do, which is a little bit more niche, was in some of the work that I've done previously, as Kaisen mentioned, had been in these generative network models. And so effectively what these models do is say, okay, let's start with an empty graph, and let's just add connections according to some rule and see what generates a network topology that's similar to what we observe. And so what we found in these spatially embedded RNNs is that these red ones do quite well. So generative models are on the x-axis. These are different candidate models of testing out. And on the y-axis is the model fit, so the lower is better. And you find these red ones, which are what we call homophily, tend to do quite well. And homophily just means preference for the self or preference for similarity. So effectively, it's based on how connected your neighbors are to each other. And this is generally, or at least what I found in some empirical network, a macroscopic diffusion, but also microscopic in vitro neural networks as well at the cellular scale. So you tend to find this kind of motif generally appears that you can fit these kind of networks because generally they form these modular kind of graphs. And you can simulate them this way. And so these spatially embedded RNNs also do this too, and the L1s do not. So there's a reason why I thought this might be interesting, and ultimately it's down to communication. It's that homophily models are the only ones of these tested that can be computed through considering it really through some local network broadcasting. Okay, so structure function. So we know that there is some spatial extent to how function occurs. And so rather than just looking at the topology per se, we wanted to look at how the activity on those neurons in this functioning RNN, whilst it's solving the task, if there's any interesting spatial patterning to those neurons, right? It might be that what you typically, this is not a question you'd normally ask in neural network research. You wouldn't typically look at the coordinate of a neuron and say, is it functioning like its neighbor? You know, it's not a kind of normal thing. But we thought maybe just by adding this kind of spatial element to it, if it would. And what we find it does, ultimately due to how it's embedded. And I was actually quite excited by it. I didn't think this would occur because it's such a simple constraint which we've added in, but it's quite neat. So what did we do? So the first thing that I did was to take the neurons of the hidden layer and decode them, just like what a lot of people would do in neuroimaging. So you effectively do a fancy way of calculating to what extent is the activity patterns on the neurons correlated to your task variable. And the task variable, remember, was goal, choices, and so on in memory. And so I did a permutation test. We would calculate how clustered or distributed the correlated activity is, more so than chance in the space. And effectively what you can see, and in this case, 0 means that you're incredibly clustered, and and 1 means that you are distributed in terms of spatial correlations to task variables. L1s have a uniform distribution of their p-values, so no general effect. But you can see quite clearly that across 1,000 networks that we trained of different regularization strengths, you have this skew for neurons that are coding goal variables to the positively skewed and negatively skewed for the choices. And so what does that mean? It basically means that over the actual task evolving, there's a spatial extent to how these neurons are coding those variables. So early on in the task, so green is your neurons which are biased towards the goal, and brown is towards the choice. And what you can hopefully see and appreciate is that early on in the task, the goal is presented, all of the neurons are green. So they're all kind of functioning or active. These are fully trained, by the way, so these are solving this task really well. Then what happens is you have a delay period, we have to memorize it, and then it gets presented with a choice, left or right. You can maybe hopefully see it from here, but effectively these green neurons are clustered in the center of this network. So they effectively are still kind of active to the goal information, whereas the distributed ones on the outside are correlated much more with the presence of the choices. And as the network goes on, it kind of tends closer towards 0. Long story short here, effectively what you're seeing is that the variables that are early on in the task, which is the goal, is kind of going into this kind of core region, which in this case, our geometry is uniform box. You could perhaps have some other priors. You could imagine that you have some different geometries here and that the neurons would become specialized in different regions. Another key point, sorry, I should mention, is that as much as I wish that we had done this, all information went to all neurons. So one of the key constraints actually in biology is that's not the case. We were talking about this earlier. So, one could speculate, just a bit like a thalamic inputs into cortex, how neurons would become specialized and learn alternative routing strategies. But in this case, at least it shows that, yes, Marcus?
So do you train those input taking weights as well? So
Yes. So
do you train those inputs to hidden weights?
no, we don't.
Okay.
No, those are fixed in these cases.
And fixed uniform or fixed?
Fixed uniform. Yeah, fixed uniform. And so that is something that we're quite interested in. So in that example, the inputs and outputs would be how you fix those or how you kind of constrain those would be very interesting. But in this case, at least we show that even in quite simple cases, you can actually get some spatial extents coming out. Now, again, another caveat, just that's a thought. This is quite a modular task. You have steps, you have stages. So that's also relevant, which we'll kind of talk about in a bit. So what I think this is one of the nicest parts of this work. I quite like it. It's quite simple, but it's a spatially organized decoded activity within the hidden layer of the neural network kind of comes out. Okay, so my collaborator, Yasha, who I'll mention towards the end, he's very interested in mixed selectivity. And particularly this idea that the classical notion of selectivity is that if you have imagine each node here, sorry, each dot on the scatter plot is a neuron, that if you have explained variance for one variable, EV1, if that increases, the explained variance for something else goes down. You know, the classic kind of tuning curve, specialization, kind of grandmother hypothesis notion, as opposed to the idea with more abstract reasoning is the idea of mixed selectivity. And there's some amazing papers, which I obviously can't talk about now, is thinking about hypothetically, why do we have mixed selective codes as opposed to this kind of purely selective? And in some sense, one of the ideas is that you can represent information in much more higher dimensions and draw a straight line through them. And some really cool things like shattering dimensionality and really, really cool work by Stefano Fusi and others. And so the idea in mixed selective codes is that effectively knowing what one neuron does doesn't really tell you too much about the other things that it could do, right? So it's a zero correlation. So on the right, in the selective case, you'd have negative correlations, where in the left, you'd have zero correlations. And so we wanted to look at that. We already know about the golden choice cases, and we just correlated them. And we did that across the 1,000 neurons that we network, and the 1,000 networks that we had for each. And what you generally find is that in the L1 networks, which are in green, that they were much more negatively correlated. So this is kind of suggesting that there was quite a lot of specialization which was kind of generated within the L1 networks, although they weren't spatially distributed, they had no concept of space. But the network activities themselves were quite negative, whereas the spatially embedded ones were much closer to this zero extent. And it's really unknown why this is. Now, one of the things that I think is clearly going to be true is this will be a function of the size of these networks. So if you have a network which is massive, you're less likely to get specialization, and so on and so forth. So if you're in a resource rational situation, you're more likely to be specialized than otherwise. One of the ideas ultimately is that it is something to do with resource rationality. And so we wanted to look at this kind of energy activity or activity in these neurons. And what we found is that in the SERNNs, if you do try and minimize their communicability, there will be less activity on those neurons. So they generally are just less active. And there are some core hypotheses about mixed selectivity linking to energy efficiency that we're kind of more interested in investigating a little bit more. But this is just a kind of an investigation into this kind of idea of mixed selectivity. Now, another idea that people were quite interested in is how can topology, network topology itself facilitate this? So is it that maybe if you have, a certain type of small world structure, does that mean that you're going to get more or less specialization? But it's still very open. And the last thing on this part is the idea of model convergence. And so I think one of the criticisms about a lot of kind of computational models is that you can tune your results to get something. But if you really want to have a good model, it should at least show a few things at the same time. They should happen in the similar parameter space, effectively. So we have two very simple parameters here, not really parameters. We have one parameter, which is the regularization strength, how much we constrain our networks. But we also have training time on the x-axis. What we effectively find is that in position 1 in the space, so if you see here, you're not really regularized very much. So what you can find is that you have no very structural constraints on the network, but it can solve the task, right? It's a fairly simple task. You can solve it, no problem. It's very dense. You can maybe just squint and see the kind of what the matrix looks like here. It's pretty dense. It's not really very modular, but it's very efficient based on the classical graph theory measures. in position 3, it's now so sparse. You've constrained this so deeply. It has so many local connections, they're symmetric, and it has basically no connections outside of the diagonal, that it can't even solve the task anymore. So you've constrained it so much. And so the idea really here is that if you push it so far that you can constrain it optimally, but still solve the task. And that'll be position 2. And it's within this position 2 where we show that we find all those findings that I was telling you earlier. So what we kind of say here ultimately is that the findings that we've shown together all kind of exist in the same spot. And this kind of speaks to this wider idea, I think, which is the kind of evolutionary landscape idea, right? You have competing constraints, and ultimately you want to find your niche where all of the things that actually were relevant for your survival did happen. And I think this is kind of where I think a lot of us are thinking about in this field. It's kind of what are the constraints that are important? Now, this is actually not just general efficiency, one could say, right? Because I think that's quite broad. It's actually mainly driven in part by what tasks organisms need to solve. But also, once they have maybe solved those tasks, you want to be able to solve those in nice ways, algorithmically or implementationally. So that's kind of how I'm thinking about that here. So just the main findings so far. Structure and function can be combined into a single model. And I think this is kind of like one way that you can do it. You could do it through evolutionary algorithms. You could also do it through supervised learning, like what we did here. And I think it's kind of a neat way of doing it. Otherwise, what we think are not kind of really related, or at least we can't directly say that they're happening in the same model system, they are occurring. So modular small world, spatial clustering of activity, decreased activations with more uncorrelated activity, and convergence in this space. And of course, we can think about what are the kind of principles we care about. And are there any things that we would want to try and recapitulate? Ultimately, you want to specify, this moves us away from thinking about how to build a model and think what are the constraints that a model system should be under, and then seeing how that would play out. And ultimately linking it to the task as well, at least in this kind of basic model. Now, that would be the main findings, but given that I thought you guys might be more interested, there's actually, of course, the supplementary stuff that no one reads. So I thought maybe you might be interested in them, and because I am, and I never actually get to talk about them. So it might lead to more discussions. So we did look at different regularizations, so not just this one. So one was in the role of constraints. So we have L1 in green, pink was the one in the main paper, which is minimizing communicability, and blue, which is minimizing the inverse of communicability. So maximizing communicability in some sense, although not separated. So that's just to keep that in mind. What you effectively see is that these blue ones don't generate the small world networks. They don't really get modular. They don't really become very modular. And there's a few other things related to skewness. So we actually looked at how skewed these weight distributions were. The way that I interpret this and think about this, although it's kind of racked my brain for a while, is that this is a summary measure, right? This is you're multiplying by multiple matrices and summing them up. The extent to which in small graphs, the way I think about this is that you have your shortest paths and your communicability can be quite correlated, right? In short paths, in short distances or small graphs. Of course, that diverges as you get to larger graphs because you now have many more indirect paths between things. But effectively, I kind of see this as a paths measure, right? It's a paths measure. So just like when you minimize shortest paths, you get efficient systems. If you minimize communicability, you're going to get something like this small worldness. But this is just minimizing it and seeing what occurs. There needs to be more formal investigations here. And I think actually, there's a lot more considerations now that we are aware of when it comes to these measures. That wasn't the case a couple of years ago. So the importance of particular communication models. Yes, Marcus?
So do you get equivalent performance for all three?
Yes, these are all in task-solving networks.
Okay, so they all perform the task to the same level.
They all perform the task to about 96%. It was the cutoff that we used. These are 100 neuron networks. So again, another consideration. Okay, this is another one. This is something different. So now what we did was also look at taking out some, so like kind of putting things in and taking them out. One of the things that maybe that I think is interesting, is actually an open problem, is when you're training recurrent neural networks of different regularizers, it's quite hard to control for some things. So what you can see, one of the limitations ultimately is that these are all for task solving networks. You can see they have different weights. They have different amount of weights in them. It's hard to control for certain things, basically, when you're training them, because effectively, I came to think about this. These are just numbers that you're minimizing. So LCE is the cross entropy, which is the task loss, but you're ultimately summing up and you're getting a number, and you want your number to be low. And so if you're adding in new terms and you're comparing different types of constraints, these are going to sum up to slightly different values. And so you're going to get, you're not going to be, your scales might be slightly off. So I think in future, it might be prudent if any of you are thinking about RNN kind of constraints. I think this is an open question on how to optimize things and do really clear apple-to-apple comparisons. I can't claim that this is perfectly good comparisons. This is a supplementary analysis of like looking at these different things under the same conditions, but you could also add different additional controls here. But the ultimate finding that I took away from this is that space, so the D-only network, hopefully you can see this is a D, it only has this distance term here. It can generate modular networks quite well. So you're getting more, modularity.
Modularity was exactly what?
This is it's the Q statistic.
The Newman weight.
Yes, yeah, yes, exactly.
And you have,
But
over time you have less and less weight. Okay.
Yes, you do, exactly. So again, one could control for there's a whole, yeah. You could control. Yes, we could discuss that afterwards, yeah. And also in small world measures, these are also binarized. So we actually controlled for densities here as well, right? So this is just to show that you can get subtle differences perhaps on the optimizations. Yeah.
Members of each module.
Yes.
I mean, for instance, a module could be just a single disconnected node,
Yep.
or how large are, is there any threshold?
So we actually had also a slide in a moment. We'll show you the Q statistic and then the number of communities that it generated.
Thank you.
Yeah. So effectively, what kind of came out from this, you can see that the communicability measures seem to be generating these higher small worldness models along with the SERNNs, but you don't really get the small worldness so much from distance alone. That's basically the thing that I wanted to kind of take across. To me, it's that you can see an observable phenomenon, and the question is what constraints can generate that. And I think the idea here is that modularity can be accounted for by quite a lot of things, including space. Yes.
Yeah, I also have a question. So I didn't understand this constraint issue. So when you have three matrices, so this circle with the dot is the Hadamard product, right?
Yes.
So and then you have L1 norm.
Yes.
Right. So, and basically you are worried that somehow if you have three matrices instead of just one, so the individual W, for example, or the individual D, so if you compare D only and SER or CERN,
yeah,
so that they are actually, if you took them out, their L1 norms would be comparable, but then the product is actually smaller because of the other matrix that is smaller somehow. So basically you haven't really, I mean, yeah, but why is that a problem?
The problem, it's just to say that effectively the scale of the loss isn't the same necessarily. It could be that your loss is a larger number that you're starting with. Now, I don't know if that's actually a major constraint, like a problem per se.
Okay.
I don't know. Like, I don't know when you're comparing, when you have two networks that you're optimizing, if that one is in the order of millions and one is in the order of tens of thousands, the number that you're actually minimizing, does that matter? Or, for example, you might want to parameterize each individual in each component individually, for example.
Yeah.
You might want to have a lambda 1, lambda 2, lambda 3.
Yeah, exactly.
This is what I'm kind of getting at.
Yeah.
So that's just a caveat that I'm kind of putting on these results here, effectively.
Yeah, so because, I mean, to minimize it, you could just minimize both individually, and then the Hadamard would also be minimal, right?
Exactly. Yes, you're minimizing both in this example.
Yes, but so it could be, I mean, just from this formulation that you just minimize one and the other one doesn't get touched, right?
That is
I mean,
possible.
but in
That is
practice,
possible. It
doesn't
doesn't,
happen.
but in principle, possible.
That is the confound that you are worried about.
Exactly.
Okay.
Exactly. And now, so actually on this point, I think there's a very interesting analysis to be done where some things are going to be easier to lose than others. So you can imagine algorithmically, from my own kind of anecdotal experience, often you kind of want to solve a problem first and then optimize it. Like how you do it. You want to do a problem first, do a really brute force way of doing something, and then find out the most efficient way to do it. So it might be that the loss of the task goes down first, and then other things come later, and so on and so forth. You could look at the timings of when things are optimized. This is something that also came up, which is I was trying to think about why would, in principle, certain topologies arise if you minimize space or if you minimize communicability. Like why? And it's very hard to know because you're just optimizing them. But this is what we talked about briefly. So again, these are very basic analyses, but for food for like further investigation. So on the top, these are two 65-node networks. Where one is randomly initialized and is asymmetric, so not having the symmetrical problem that you were saying. And effectively, then the same network in terms of the density, in terms of the number of nodes, but now has been made into more of a hierarchical network. You can see this kind of modules popping out, and it has this kind of ring structure. And effectively, if you sum up the communicability of those two networks, this one is lower. Right, so this is the box plot here. If you summarize this, so if you just add in all the elements of this matrix. Now, this is kind of in my mind going back to that finding I showed you earlier that they have lower activations, and under this kind of idea that a random walker is, you can kind of think of them as particles of like just signaling. Right. If there is a cost to this, if there is a cost to communication, are there certain topologies that you would more likely find? Right. So in this analysis, you can see that effectively same network, although it's been arranged differently topologically, this one has less communicability. That's it in a nutshell. And so the way I kind of think about this, if there is a cost to communication, if there is a cost to this, i.e. it has been minimized in our models, but if there's a cost to sending signals, maybe a certain type of topological structure would be more preferable. Right. But again, open, it's the kind of idea of like putting a constraint. If that is costly, what would you see? Another is the weights. So this is a little bit of a complicated chart, but it's related to under this weighted communicability measure. If you normalize it, if you increase some weights here, the communicability will decrease. Each line is an edge here, by the way. Each line is an edge. So if I increase this edge, whatever this edge is, this line, the total weighted communicability goes down. Although in other cases, you strengthen them and it goes up. What you basically find is if you normalize your random walker based on the node strengths, which I do here, although again, we can talk about if this is a good or bad, what you'll basically find is that these edges which are more in the quote unquote core of the network will become strengthened. The weights will actually go towards those. And the edges on the outside will be weakened. This is trying to get at what, if you optimize a network for a particular property, what happens to the arrangement of the weights on the graph as opposed to anything else. And the analogy that I think about this is, at the moment right now, I'm speaking. And so all the weights are kind of coming into me, right? And as a result, the total communication in this room compared to what it could be is lower, right? I'm sucking up all the normalized communicability here. Whereas if we were all talking to each other in a segregated way, where the weights are stronger between us, the total, if you summed up the matrix of our room, the normalized communicability would be higher under this measure. But if you don't do this normalization, you don't have this relativity idea, relative weights. So it goes into a little bit of a deeper question about the communication models, which we'll talk about perhaps later. So minimizing this normalized communicability term will strengthen weights in these kind of topologically central regions and weaken them in the outside. And so basically this is me trying to get at why would these RNNs, when you optimize them, have particular weighted structures? What you'd hypothesize is maybe you would have this kind of modular structures, but the weights would actually be more on those edges that are kind of more central. So I think this kind of way of thinking is something I'm quite interested in, is like what happens to the weights and the communication models and maybe more to dynamics as you optimize these networks to do something given a constraint. Yes.
So I see a bit of a hen and an egg problem here, maybe, because so you're saying that minimizing a normalized communicability term will strengthen weights in topologically central locations. So I'm just reading from your from a slide. So okay, so you will strengthen weights in topologically central locations. So you mean you already have something topologically central before you do your optimization?
It would be whatever it was before.
So
you could randomly initialize it, for example. Ultimately, from what I'm trying to say here, I think is that if you have any network and you're trying to minimize some quantity, right, and you're going down this new landscape that you're trying to minimize, what will happen to the weights? And you'll basically find that because your communicability is a function of the graph, it will take the graph into account, and whatever those are central now will become stronger. That's what I'm saying. So yeah, you may have, it might be random to start with because of how gradient descent works in this case, but then once it's kind of found that, it will kind of keep on doing it.
Oh, okay. And then it really depends on the graph initialization, of
Exactly.
course.
So then definitely initialization will have a big effect for certain. You could initialize this randomly, which we did, but initialization is going to have a bigger impact actually, particularly if you initialize, and this goes again to, these initial conditions will have a massive effect. Yeah, totally.
Okay, thank you.
Okay, so again, away from the constraints, two more on the actual task. So I said before, you can make this task harder. And so one of the reviewers asked us for this, and Fatima, you asked about the size of the communities. And so what we did was just simply one task difficulty was simply just to make this shorter or longer, the task. And so we can imagine we can make this in discrete time, we make this shorter or longer. Gold is short, pink is what we did, and blue is long. What you basically find, no surprise, the easy task here, all the networks can do because it's quite easy. And of the 1,000, only about 100 could do the difficult task, which makes sense. But what's interesting is that the easy tasks can be done by networks with an average size of their modules that's quite large. So they can be done by bigger modules, as opposed to in our models here, the moment you make this harder, the average size came to about 2 or 3. So you'll basically have a Q statistic, which is fairly comparable, but the modules are much smaller. And so I don't know if there's any idea about this, about the notion of difficulty and size of modules and this kind of thing, but that was something that I think pointed to that in this work. Again, it's something that I really want to do more of, like thinking about task difficulty, and also the fact that anything can do the easy, but only a very particular type of network could do the hard ones. Yeah. Yes.
So I have another comment about this. So if you have an easy task, you have many modules. So, and the networks have a fixed size, right?
Yep.
So, and that maybe means that your network was too big. So the question is a little bit, I suspect, what's the intrinsic dimensionality of the task? And that might then, so like say it's K, like you need K dimensions somehow of neural activity. And then it would mean you could probably do it with K neurons. And so I suspect that, now if you have n neurons and you have 15 modules, so n divided by 15 should be close to K.
So it requires, you're saying that basically that so in this task, would the difficulty change the dimensions required? I don't really know about,
I'm not sure, I'd have to think about it, but there is this work by Susilo, and Susilo is the last author, and Nilu is the first name of the first author. I don't know the last name. I think Manis Varanathanos or something like that. And there they actually show, that's related, that very different networks have actually very similar intrinsic dimensionality, and that when they have to solve the task, and so the dimension they kind of form is based on the task dimension, and I suspect maybe something like that might be going on here.
Yeah, perhaps. Again, one of the things we never did was, which again would be quite useful when thinking about, again, the spectral properties of these networks, which you also did look at, is the dynamics of the networks, basically. One of the things that we were chatting about earlier is that in these networks, they become more symmetrical in the spatial ones. And the reason is because space is symmetrical matrix. So when you try and constrain a network by that D matrix, the spectral properties change, and that will change the dynamics itself. clearly. So that's something that we never even did that. It's quite a simple task, but we never looked at that. It's a fairly simple task, so I think it would be quite straightforward, actually. You feel free to have the data if you want and do the analysis on that. And the last one was effectively noise. We just added in noise into these networks as well. And effectively what you find, the only effect that really you could see is that they become less modular as you added more noise. And the way I have this general, this general notion of the task should shape the network in some way. So perhaps increased noise would lead to these modular networks. Again, the point was to say that this is like I'm just throwing these out because it hasn't been rigorously done yet, but I think this kind of deserves it, some of this kind of work. Okay. So ultimately, I think, the kind of idea that I'm kind of going with these is to ultimately think about what are the constraints within the network itself. So kind of within the agent. So like, what is there cost to communication? Is there a cost to computation? What are the priors that are operating on that network? Particular input, or should we model particular inputs within certain cases? And then, of course, the other thing, the elephant in the room, is the task. So you've got the things in the environment. So what's the structure in that environment? Is it noisy? Is it not noisy? What are the kind of problems that you want to solve? Could be the interaction between other agents, or broad tasks that must be solved, like just general environmental or very specific tasks that might be solved. And of course, there's this kind of drive for evolutionary developmental solutions. There might be loads of solutions to this. And so this is kind of, it's a big mess. And so trying to these kind of early ones are just kind of us trying to have this model, which is spatial, and then trying to vary these task requirements. But of course, it's in a very simplistic way. But I think this is one way to do it, and kind of do a farmyard of this, like loads of tasks and how all these parameters change the structure. And so these are some of the questions I'm interested in. Kind of what are the kind of topologies that could arise from common tasks and dynamics alongside that, and how may randomness actually be useful? Okay, so that was the longest part of the talk, probably another 10 minutes, 5-10 minutes or something like this, which is a bit more of a speculative idea that I think maybe might be of interest, which is on delays. So here we kind of treated this space as a cost. And I know that in this group, in your group in particular, this idea of adding in biological priors should never really improve performance, because like random networks are kind of efficient, and they are expensive, quote unquote. And so why would anything do better than that? And so this is kind of in line with this, space is a cost, you have to solve it. And that's why geometry, interestingly, is not interesting here, because it's a D matrix. And so you're just trying to minimize it. So if you tried to minimize, if rather than minimizing the Euclidean distance matrix, you tried to minimize you had coordinates as the learnable parameter, like it can move the neurons, you can imagine it would move them all towards 0. Like they would just push them into 1, because there's no benefit of space at all. It's just a cost to be overcome. But I've been really interested in these papers that have been coming from physiologists, which talk a lot about timing and conductance. And so this is a really cool paper called Myelin as the Gateway to Learning by Bonetto et al. In Cambridge. And the basic essence is that we know that kind of conductance is driven by this kind of idea of the G ratio, which is your axonal diameter to your kind of total myelin fiber diameter. But you would think the textbook way that we learn at school, well, at least I internalized it, is that the kind of more myelin, the better, because it makes things quick. So that's good. But this work is really interesting. So they actually put forward that myelin is highly plastic. We tend to think of myelin as being very static. And that also, it's not always the more myelin, the better, that there's actually some kind of relatively optimal myelin that can change at very quick timescales. These are people saying at the level of kind of minutes, even. So it's quite interesting. That's not the most interesting bit for me here. The more interesting bit is actually the idea that one could, in principle, alter myelination as to maximize your coincidence inputs. So you can imagine here you have a neuron A to C, neuron B to C. If A and B fire, you don't elicit a coincidence action potential here because there's maybe some relative differences in the timing propagation going on. But you can imagine that learning is not necessarily the weight of the synapses they put forward. It's actually that it's the alternate, just changing of the conductance speeds that's important. And that you can actually you can optimize, quote unquote, the speeds, and that actually can maybe generate coincidence inputs. And so this is kind of their hypothesis for learning. However, there's no easy way. They don't know how it would be, quote unquote, optimized. There's no obvious way that how would one optimize this biologically, right? But it's an interesting hypothesis. And so, of course, when you think about space, you can think about the heterogeneity to conductance delays between regions. This kind of was an idea that was actually put by Eugene Zikovic in 2006, which is this idea of polychronicity, which I'll just talk about very briefly, because I think it's really interesting. And lots of people have looked at this in the computational neuroscience community. The idea is that space is not a cost, it's an actual major benefit. And the basic reason why is because in this example here, where you have a feed-forward neural network here of different delay speeds that could be proportional to distance in this example, you can see that if B, C, then D fires in a sequence, so you're not just given an input per se, you're given a sequence of inputs. Because of the delays, E will fire, right? So if you go B, then C, then D, E fires. If D, then C, then B fires, then A fires. Hopefully you can see that because of the relative delays. This is longer and therefore takes longer when the spike actually will arrive at the same time. And so just because you have delays ultimately means that you can have sequence detection. A is now not a coincidence detector per se, it's actually a sequence detector for particular inputs. And as a result, actually, by embedding them in space and therefore conductance delays, there might be some benefits that you don't necessarily need maybe recurrence to require sequences. You can actually just have space or heterogeneity of space. And so actually there's this cool paper that he did in 2006, which I'd recommend you have a little look at, which is where what he does is look at spike timing dependent plasticity as a local learning rule. Where effectively timing matters. If your pre fires before your post, you strengthen and vice versa. You can generate what he calls polychronic groups. So polychronic group is an idea that if you have delays between neurons, you'll have a reliable sequence of neurons which would always fire to a particular sequence. So you could have a sequence of inputs, and then neurons will then spike for a little while, and that will be specific to the sequence of inputs. Effectively, a memory for sequences. It's effectively what it is. And that would include inhibitory. And what you can find is that for any arbitrary number of sequences, you would get polychronic groups. They would have a size. There'd be a number of them. They would have a particular temporal span. They would be sensitive to particular inputs and temporal aspects of those inputs. And what he puts forward in there is it's very interesting because there's many polychronic groups that could emerge. You can have many polychronic groups to arbitrary number of sequences that are nearly infinite because you can have they're time resolved. So you can have overlapping polychronic groups. You can have a single neuron is part of many polychronic groups simultaneously. So it's kind of resonant to this dynamic modularity or mixed selectivity kind of idea. And effectively, in these models, he kind of thinks of them as memory, as some polychronic representation. Now it's not a sequence. It's actually like it's relative to the delays, and your strengthening is you being sensitive and actually being assigned to that memory. So it's this kind of idea of memory assignment and so on. And it will naturally, what I think is kind of interesting about it is that it links in topology directly into learning. So the topology and the location of neurons and the learning rule are all crucial. And so some of the work that I've been kind of doing is thinking about space in this model. So these models don't typically look at space, but I've started off on looking at spatially embedded spiking models, effectively, not optimizing through tasks, but a lot more just stimulating them with pulse-coupled synapses. It gets really complicated when you actually add conductance-based synapses. Yeah, so I'm kind of looking a little bit about this. And so the idea really being that if there is an empirical conductance speed, space is not arbitrary. Space is actually crucially important, and maybe it's beneficial. Because you have heterogeneity of delays. And it makes me think a little bit about kind of the spatial elements. It's a bit more speculative, but you can actually think about if there is a benefit to space and you can build it into an artificial system, that it's something to do with heterogeneity of timings that can capture representations in a temporal signal. Maybe actually you would build, your network would actually grow a coordinate space and it would be beneficial and could work within a particular constraint. So that's the speculative idea. The links that. Cool. So that's nearly it, basically. So just conclusions. So I think that, yeah, building in the constraints of the models could be a useful bridge. It could inspire new architectures or principles within artificial systems. I'm not saying that I think that it will improve, but I think that this idea of delays might be one way that it could help improve, particularly if there's some resource rationality ideas coming in. And yet, as I said before, future models hopefully should incorporate more specific principles. The spatially embedded RNNs we published last year. And so you can use the code as well. We have it all open to you to look at. So I did the paper with Jesha Achterberg. We co-led it together in our PhDs. And our supervisors, Duncan Asselland and John Duncan, and my two students who are doing new stuff, which is cool. And if anyone, I will hopefully be recruiting a postdoc soon in Cambridge. Oh, no, not in Cambridge, in Imperial. And so if you want to kind of join, a few of us will be there. It'll be for 18 months, but minimum. So hopefully looking to extend it. And that'll be based in Imperial with Dan Goodman and myself. So thank you.